Have you ever looked up at the night sky and felt the weight of infinity pressing down? Stars scattered like dust across velvet darkness, galaxies swirling in the deep, each point of light a sun, a world, a story written in fire and time. But what you see, what any of us can see, is just the smallest fragment of what exists. We speak the word universe as if we know its boundaries, as if our telescopes have mapped every corner, every shadow. But the truth is quieter and stranger. We live inside a bubble, a sphere of visibility carved from the vastness by nothing more than time and light. Beyond that edge lies everything we can never know, never touch, never see. Tonight, we drift toward that boundary, that cosmic horizon, to ask not just what lies beyond, but why the universe chose to hide it from us. So close your eyes, let the darkness settle like a blanket, and follow me to the edge of everything we can see. Before we begin, if you're kind enough, a gentle like or a quiet tap on subscribe would mean the world to me. It's a small gesture, but I hold it with deep gratitude because every bit of your support keeps this tiny universe alive and reminds me that these quiet stories still find their way to gentle hearts like yours. Now, let's begin with the first question. Part 1. How big is our cosmic bubble? When astronomers talk about the observable universe, they're describing a sphere centered on Earth, a bubble of visibility stretching 46.5 billion light years in every direction. That number might sound impossible at first. After all, the universe is only 13.8 billion years old. How can we see farther than light has had time to travel? The answer lies in expansion, in the way space itself has been growing since the moment of the Big Bang. According to NASA's Goddard Space Flight Center, light from the most distant objects we can observe has been traveling toward us for nearly the entire age of the universe. But while that light was in transit, space was stretching, carrying those distant sources farther and farther away. The galaxies we see at the edge of the observable universe are no longer where they appear to be. They've been swept away by expansion, pushed beyond our cosmic horizon into regions we can never observe. This boundary, this edge of visibility, isn't a physical barrier. It's a limit imposed by time itself. Light travels at 186,000 miles per second, the ultimate speed limit of the universe. Nothing can move faster through space, but space itself isn't bound by that rule. Space can expand faster, then light can cross it, creating regions forever beyond our reach. ESA's Planck satellite has mapped this cosmic horizon with extraordinary precision, measuring the cosmic microwave background, the faint afterglow of the Big Bang that marks the furthest light we can ever detect. That ancient light has been traveling for 13.8 billion years, stretched by expansion from high-energy gamma rays into gentle microwaves. When we observe it, we're looking back to a time just 380,000 years after the universe began, when space first became transparent to light. Before that moment, the universe was an opaque plasma, too hot and dense for light to travel freely. The cosmic microwave background is the wall at the edge of our vision, the oldest light that exists. But here's the profound mystery. Our cosmic bubble isn't the only one. Every point in space has its own observable universe, its own sphere of visibility. An alien civilization in a galaxy 10 billion light years away would see a different cosmic horizon centered on them. Some galaxies they observe would be invisible to us, and some we see would lie beyond their view. The observable universe, in this sense, is personal, unique to each observer's position in space and time. The James Webb Space Telescope, JWST, has pushed deeper into this cosmic bubble than ever before. It has captured galaxies that formed just 300 million years after the Big Bang, their light redshifted and ancient, stretched by billions of years of expansion. These early galaxies appear as they were in the universe's infancy, small and irregular, still condensing from primordial gas. Some are among the most distant objects ever observed, yet they're still well within our cosmic horizon. Beyond them, farther than our telescopes can reach, lie galaxies we will never see, not because they're too faint or too far, but because their light hasn't had time to reach us yet, and some never will. The expansion of space is accelerating, driven by dark energy, a mysterious force that pushes the fabric of the cosmos apart. According to ESA's Euclid mission, launched in 2023, dark energy makes up about 68% of the universe's total energy. Its presence means that distant galaxies are receding faster and faster, and some regions are moving away so quickly that their light will never cross the growing gulf of space between us. This creates a second boundary, more permanent than the first. It's called the cosmic event horizon, and it marks the limit beyond which events can never affect us. Galaxies beyond this horizon are causally disconnected, separated not by distance alone, but by the structure of space-time itself. Even if we waited forever, even if the universe aged 1 trillion years, their light would never arrive. They exist in a part of reality we are fundamentally cut off from. So our cosmic bubble has two edges: the particle horizon, defined by how far light has traveled since the Big Bang, and the event horizon, defined by the accelerating expansion that severs causal connections. Between these boundaries lies everything we can ever hope to observe, a vast but finite region of space containing perhaps 2 trillion galaxies, each with hundreds of billions of stars. It sounds immense, and it is, but compared to the totality of space, it might be nothing more than a grain of sand on an infinite beach. As cosmologist Brian Greene once said, "We are living inside a cosmic bubble, and we can never know what lies beyond its walls. Our sphere of visibility is all we have, all we will ever have. And yet, knowing this limitation, we can't help but wonder, what exists out there, beyond the edge? What galaxies swirl in the darkness we can never see? What civilizations might thrive, forever unaware of our existence as we are of theirs?" Take a slow breath. Right now, as you sit here, the edge of the observable universe is rushing away at unimaginable speed. New regions of space are slipping beyond our horizon every moment, galaxies winking out of visibility as expansion carries them past the point of no return. The universe we can see is shrinking in a sense, even as the universe as a whole continues to grow. And as we ponder this vanishing vista, another question rises, quiet and persistent. If we can only see a bubble, a fragment of the whole, then how big is the universe really? Does it go on forever, or does it have an edge of its own? That's where we turn next. Part 2. Is the universe infinite, or does it have an end? The question feels almost too large to ask. Does the universe have an edge, a final boundary beyond which there is nothing? Or does space stretch on forever, an endless expanse without beginning or end? For millennia, philosophers and thinkers have wrestled with infinity, and even today, with telescopes that peer billions of light years into space, we still don't know the answer. According to Einstein's general theory of relativity, the shape and size of the universe depend on its contents. If the universe contains enough mass and energy, gravity will curve space into a closed shape, like the surface of a sphere. In such a universe, you could travel in one direction and eventually return to your starting point, never encountering an edge. It would be finite in size but without boundaries. Just as the surface of Earth is finite, but has no edge you can fall off. But if the universe contains less mass and energy, space curves differently, creating an open, saddle-shaped geometry. In this scenario, space would be infinite, stretching forever in all directions. Between these extremes lies a flat universe, where space follows the familiar geometry we learn in school. A flat universe could be either infinite or finite, depending on its topology, the way space connects to itself on the largest scales. So which is it? Observations from ESA's Planck satellite have measured the curvature of space with extraordinary precision. The data shows that the universe is remarkably flat, so flat that any curvature lies beyond our ability to detect. According to NASA's WMAP mission, this flatness suggests the universe might be infinite, extending forever beyond our cosmic horizon. But flat doesn't necessarily mean infinite. Space could be flat and yet finite, wrapped into complex topological shapes. Imagine living on the surface of a three-dimensional torus, a donut shape. Locally, the geometry would appear flat, but the surface itself would be finite, looping back on itself. The universe could be shaped this way, though the loops would be so vast we might never detect them. Light traveling in a straight line could, in principle, circle the cosmos and return from the opposite direction, allowing us to see the same distant galaxies from multiple angles. In 2003, astrophysicist Jean-Pierre Luminet proposed that the universe might have the topology of a Poincare dodecahedron, a 12-faced shape where opposite faces connect. If true, we might detect repeating patterns in the distribution of galaxies, subtle echoes where the same structures appear in different parts of the sky. Searches using data from the Sloan Digital Sky Survey have found no conclusive evidence, but the possibility remains open. NASA's upcoming Nancy Grace Roman Space Telescope will map the universe with unprecedented precision, searching for these topological signatures. If space loops back on itself, the statistics of galaxy clustering might reveal faint patterns, hints that the universe is finite but boundless. Yet, if the universe is truly infinite, the implications are staggering. An infinite universe means infinite matter, infinite galaxies, infinite stars. It means that every possible arrangement of atoms, every variation of history, must occur somewhere. In an infinite cosmos, there would be countless copies of Earth, countless versions of you, living lives identical to yours or subtly different. This isn't science fiction. It's a logical consequence of infinity combined with the finite number of ways matter can arrange itself. Cosmologist Max Tegmark has calculated that in an infinite universe, there should be another Earth, nearly identical to ours, about 10 to the power of 10 to 29 meters away. That distance is so vast it makes the observable universe seem microscopic. These duplicate worlds exist if the universe is infinite, but they lie forever beyond our horizon, unreachable and unknowable. The idea is both wondrous and unsettling. If space goes on forever, then nothing is unique. Every moment, every choice, every life is repeated endlessly across the infinite expanse. Somewhere, far beyond what we can see, another version of you is reading these same words, or perhaps making a different choice, living a different life. But there's a deeper mystery. Even if the universe is infinite now, it wasn't always infinite. Or rather, if space is infinite today, it must have been infinite at the moment of the Big Bang, just compressed into a denser state. Infinity doesn't grow or shrink. It remains infinite through all transformations. The Big Bang, in this view, wasn't an explosion from a point. It was an expansion of all of space, happening everywhere at once. As physicist Sean Carroll explains, the Big Bang is not an explosion in space, but an explosion of space. If the universe is infinite, then the Big Bang occurred across an infinite volume, filling all of existence with energy and matter. This challenges our intuition, which wants to picture the universe beginning at a single point, but relativity tells us otherwise. ESA's Euclid mission, mapping billions of galaxies, will measure the large-scale structure of the cosmos with exquisite detail. By studying how galaxies cluster and how light bends through space, scientists hope to constrain the universe's geometry and topology. If patterns emerge, if subtle repetitions appear in the cosmic web, we might learn that space is finite after all, wrapped into a shape too large to see directly but detectable through its effects. For now, the question remains open. The universe might be infinite, a boundless expanse stretching forever beyond our tiny bubble of visibility. Or it might be finite, wrapped into a shape so vast that even light, traveling for billions of years, hasn't yet revealed its curvature. Either possibility is profound. Either way, we are small, confined to our cosmic horizon, gazing outward at a mystery we may never solve. Take a quiet breath. The universe, whether infinite or merely unimaginably large, surrounds you on all sides. Beyond the stars you can see, beyond the galaxies our telescopes capture, space continues, filled or empty, finite or endless, holding secrets we can only imagine. And as we consider this vastness, another question emerges. If our cosmic bubble is expanding, if the edge of what we can see is moving outward, what lies in the space we haven't seen yet? Is it filled with galaxies like ours? Or is there something stranger waiting in the darkness? That's where we drift next. Part 3. What exists beyond our cosmic horizon? The edge of the observable universe isn't a wall. It's a horizon, like the horizon at sea, defined not by a physical boundary, but by the limits of our vision. Just as you can't see beyond the curve of the earth, we can't see beyond the sphere of light that has had time to reach us. But unlike the ocean, where you can sail toward the horizon and reveal what lies beyond, the cosmic horizon is different. It's defined by time and expansion, and no matter how long we wait, some regions will forever remain hidden. So what lies beyond? The simplest answer, supported by observations from NASA's Hubble Space Telescope and JWST, is more of the same. More galaxies, more stars, more planets. The universe, as far as we can tell, is homogeneous on the largest scales. This principle, called the cosmological principle, states that the universe looks roughly the same in all directions and at all locations. There are no special places, no cosmic centers. If you could somehow jump to a galaxy 20 billion light years away, the universe around you would look similar to what we see here. Clusters of galaxies, vast voids, filaments of matter stretching across space. ESA's Planck satellite confirmed this homogeneity by mapping the cosmic microwave background. The ancient light shows tiny variations, seeds of structure that grew into galaxies, but overall, it's astonishingly uniform. This uniformity suggests that beyond our horizon, space continues much as it does within it, filled with matter and energy, evolving according to the same physical laws. But there's a catch. The regions beyond our horizon are not just far away, they're causally disconnected. Events happening there can never influence us, and we can never influence them. They exist in a separate part of space-time, cut off not by distance, but by the structure of the cosmos itself. In a sense, they're like parallel realities, not in the science fiction sense of alternate timelines, but in the sense that they're parts of the same universe that can never interact. This separation is enforced by the expansion of space. According to measurements by NASA's Chandra X-ray Observatory and ESA's XMM Newton mission, the universe is expanding at about 70 kilometers per second per megaparsec. That means for every 3.26 million light years of distance, space is growing at 70 kilometers per second. At large enough distances, this expansion exceeds the speed of light. Galaxies billions of light years away are receding faster than light can travel, not because they're moving through space, but because space itself is stretching. This creates a peculiar effect. Light from those distant galaxies can still reach us because it's traveling through space toward us. But new light emitted today from galaxies beyond a certain distance will never arrive. The expansion carries them away faster than their light can close the gap. These galaxies are slipping beyond our cosmic event horizon, the boundary beyond which causal contact is impossible. As astrophysicist Neil deGrasse Tyson once said, "The universe is not only stranger than we imagine, it's stranger than we can imagine." The regions beyond our horizon might contain wonders we can't conceive, but we'll never know. They're lost to us, not destroyed but rendered forever invisible by the geometry of expanding space. Yet, there are hints, suggestions, that not everything beyond our horizon is identical to what we see. Some cosmological models propose that the universe might have different properties in different regions. These models, emerging from the theory of eternal inflation, suggest that space didn't expand uniformly everywhere. In some regions, inflation ended early, creating pockets where galaxies and stars formed. In others, it continues, driving exponential expansion. According to physicist Alan Guth, who proposed inflation theory in 1981, our observable universe might be just one bubble in a vast, eternally inflating multiverse. Each bubble would have its own physical constants, its own laws of nature. In some bubbles, stars might form differently. In others, atoms might not exist at all. These bubble universes would be separated by vast inflating regions, making contact between them impossible. If true, then beyond our cosmic horizon might lie not just more galaxies, but fundamentally different realms of existence. Our observable universe would be like a single island in an infinite ocean, surrounded by other islands we can never reach or even detect. NASA's observations of the cosmic microwave background have searched for signs of collisions between bubble universes, circular patterns that might indicate our bubble once touched another. So far, no conclusive evidence has been found, but the search continues. There's also the question of dark energy. This mysterious force driving the accelerated expansion of space makes up about 68% of the universe's energy. According to ESA's Euclid mission, dark energy appears constant across space and time, at least within our observable region. But does it remain constant beyond our horizon? Could there be regions where dark energy is stronger or weaker, where expansion happens at different rates? Some physicists, including Lawrence Krauss and Brian Greene, have speculated that dark energy might vary across the cosmos. If so, the universe beyond our horizon might be expanding faster or slower than our region. In areas where dark energy is weaker, galaxies might cluster more densely, forming structures we can't observe. In areas where it's stronger, space might be nearly empty, with galaxies so spread out that stars never formed. These ideas remain theoretical. We have no direct evidence of variation in dark energy or differences in physical laws beyond our horizon. But the mere possibility reminds us how limited our view is. The observable universe, vast as it seems, might be just one configuration among infinite variations, a single note in a cosmic symphony we can barely hear. The James Webb Space Telescope continues to push the boundaries of what we can see, capturing galaxies at the edge of our cosmic bubble. But even JWST, with its infrared eyes, can't see beyond the particle horizon. No telescope ever will. The light from those regions hasn't arrived yet, and if current models are correct, much of it never will. The expansion of space ensures that some parts of the cosmos will remain forever hidden, their stories untold, their light never reaching our eyes. Take a slow breath. Beyond the edge of what you can see, beyond the farthest galaxy our telescopes capture, space continues. It might be filled with wonders or emptiness, structures like ours or realms utterly alien. We'll never know. The cosmic horizon is a one-way mirror, letting us see out to a point but revealing nothing of what lies beyond. And as we sit with this unknowing, another question arises. If the universe is hiding so much from us, if vast regions are forever beyond our reach, then what does it mean to understand the cosmos? Can we ever claim to know the universe when we've only seen a fraction? That's where our next chapter begins. Part 4. Why can we never see beyond the edge? The edge of the observable universe isn't just far away, it's fundamentally unreachable, not because of technological limitations, but because of the structure of space-time itself. No telescope, no matter how powerful, can ever see beyond it. The reason lies in the interplay of light, time, and expansion. Three forces that conspire to create an absolute boundary on our knowledge. Light travels at 6,000 miles per second, the ultimate cosmic speed limit. According to Einstein's special theory of relativity, nothing can move faster through space. This speed limit isn't arbitrary. It's woven into the fabric of space-time, a consequence of how space and time relate to each other. Photons, particles of light, travel at this maximum speed, and they set the pace for how quickly information can move from one place to another. But here's the constraint. The universe is only 13.8 billion years old. That means light from the Big Bang has only had 13.8 billion years to travel. You might think this creates an observable universe, a 13.8 billion light years in radius, but expansion complicates things. While light was traveling toward us, space was stretching, carrying the sources of that light farther away. The result is that the edge of the observable universe now lies about 46.5 billion light years away, according to NASA's Goddard Space Flight Center. This boundary, the particle horizon, marks the limit of what we can ever see. Beyond it lie regions whose light hasn't had time to reach us yet. In a static universe, we could simply wait. Given enough time, light from those regions would eventually arrive. But the universe isn't static. It's expanding, and that expansion is accelerating. Dark energy, the mysterious force driving this acceleration, changes everything. According to measurements by ESA's Planck satellite and NASA's Dark Energy Survey, dark energy pushes space apart faster and faster. This means that distant galaxies are receding at ever-increasing speeds. At large enough distances, they're moving away faster than light can travel toward us. Light from these galaxies is fighting a losing battle, trying to cross a gap that's widening faster than it can bridge. This creates a second boundary, the cosmic event horizon. Galaxies beyond this horizon are receding so fast that their light will never reach us, no matter how long we wait. If we could watch one of these galaxies, we'd see it freeze at the boundary, red shifted to invisibility as expansion carries it away. From our perspective, it would fade from view, not because it stopped shining, but because space itself pulled it beyond the reach of light. As physicist Kip Thorne explains, the universe has a fundamental limit on what we can know, not because of our technology, but because of the nature of space and time. This limit is absolute. Even if we develop perfect telescopes, even if we could detect individual photons from the most distant sources, we still couldn't see beyond the event horizon. The information simply can't reach us. But there's another layer to this mystery. Even if we could somehow see beyond the horizon, what would we be looking at? When we observe distant galaxies, we're not seeing them as they are now. We're seeing them as they were when their light left them. The farther away a galaxy is, the farther back in time we're looking. At the edge of the observable universe, we're seeing light from galaxies as they appeared just a few 100 million years after the Big Bang. Those galaxies, if they still exist, have evolved, changed, perhaps collided with others, or been torn apart by cosmic forces. We'll never know, because the light showing their current state hasn't reached us yet, and never will. This creates a strange disconnect. The universe we observe is a mosaic of different times, different eras, stitched together by the journey of light across expanding space. The cosmic microwave background shows us the universe at 380,000 years old. The most distant galaxies captured by JWST show us cosmic structure at a few 100 million years. Closer galaxies reveal more recent times, and the Milky Way, our home, shows us the universe as it is now, or at least as it was a few tens of thousands of years ago. The time it takes light to cross our galaxy. We're living in the present, but we're surrounded by images from the past, echoes of light that left their sources eons ago. The universe we see is not the universe as it is. It's a historical record, a light speed delay built into the very nature of observation. And beyond the edge of what we can see lies not just more space, but more time. Futures we can never witness. Presents we can never confirm. NASA's upcoming missions, including the Habitable Worlds Observatory and advanced gravitational wave detectors, will probe the observable universe with greater precision. But they won't extend the fundamental boundary. They'll reveal more detail within our cosmic bubble. But the edge will remain where it is, defined not by our instruments, but by the age of the universe and the speed of light. Some physicists have proposed clever workarounds. If faster than light travel were possible, if wormholes or warp drives could be created, we might bypass the limitations of expansion. But these ideas, while mathematically intriguing, require exotic physics we've never observed, like negative energy or stable wormholes. According to general relativity, such structures might exist in theory, but creating them would require technology far beyond anything we can imagine. Even if we could travel faster than light, the cosmic event horizon would still exist. We might be able to visit regions beyond it, but we could never return. The expansion would trap us there, severing our connection to home, and any information we gathered would be stuck with us, unable to reach back across the expanding gulf. So the edge of the observable universe is a true boundary, not a temporary limitation, but a fundamental horizon written into the structure of reality. We can study it, map it, measure the galaxies near it, but we can never cross it or see beyond it. It's the universe's way of keeping secrets, of ensuring that some mysteries remain forever unsolved. Take a quiet breath. Right now, at this very moment, galaxies are slipping beyond the cosmic horizon. Their light, which has been traveling toward us for billions of years, is being stretched and redshifted, fading from view as expansion carries them past the point of no return. We're watching the universe shrink in a sense, not because it's getting smaller, but because more and more of it is becoming forever unreachable. And as we sit with this limitation, this cosmic blindness, a final question emerges. If we can never see beyond the edge, if vast regions are hidden from us forever, then what does this mean for our understanding of existence itself? Are we truly isolated, confined to our bubble with no hope of ever knowing what lies beyond? That's where our last chapter takes us. Part 5. What does it mean to live in a cosmic bubble? We live inside a sphere of light, a bubble carved from infinity by the simple fact that the universe has an age and light has a speed. Everything we can ever see, every galaxy, every star, every photon, lies within this sphere. Beyond it stretches the unknown, regions of space we will never explore, never observe, never understand. What does it mean to live with this knowledge? To know that the cosmos is larger than what we can experience? For some, the cosmic horizon is a source of wonder. It reminds us of our place in the universe, small and temporary, witnesses to a fragment of something vast. Astronomer Carl Sagan once said, "We are a way for the universe to know itself. Our cosmic bubble is the stage on which that knowing happens, the region where light, matter, and consciousness intersect. Within this bubble, atoms formed, stars ignited, planets cooled, and life emerged. It's our home, our only home, the only place where the universe becomes aware of its own existence. But the bubble is also a reminder of limits. No matter how advanced our technology becomes, no matter how deeply we probe the cosmos, we can never escape the fundamental boundary imposed by space-time. This isn't a failure of imagination or engineering. It's a law of nature, as unbreakable as the speed of light or the conservation of energy. According to physicist Sean Carroll, the universe doesn't owe us comprehensibility. There are things we can know and things we can't, and the edge of the observable universe marks that boundary. Yet, knowing we live in a bubble also shapes how we think about existence. If our observable universe is just one region among countless others, if space continues far beyond what we can see, then everything we observe might be just a local phenomenon, a single patch of reality with its own properties. The laws of physics we've discovered, the constants we've measured, the structures we've mapped, all might be specific to our bubble, not universal truths, but local conditions. This idea emerges from theories of eternal inflation proposed by physicist Alan Guth and refined by Andre Linde and others. According to NASA's Wilkinson Microwave Anisotropy Probe, WMAE, the cosmic microwave background shows patterns consistent with inflation, a brief period of exponential expansion that smoothed the early universe. But if inflation happened once, it might happen eternally in some regions, creating countless bubble universes, each with its own physics. In this framework, our cosmic bubble is just one among a vast, perhaps infinite ensemble. Other bubbles might have different values for fundamental constants like the strength of gravity or the mass of the electron. Some might form galaxies and stars. Others might remain empty, unable to create complexity. Our bubble happens to have conditions suitable for life, which is why we're here to observe it. This reasoning, called the anthropic principle, suggests that the universe isn't fine-tuned for life. We simply find ourselves in one of the rare regions where life is possible. ESA's Euclid mission, mapping the large-scale structure of the cosmos, will search for hints of this multiverse. If our bubble once collided with another, it might have left a mark on the cosmic microwave background, a circular pattern or anomaly. So far, no conclusive evidence has been found, but the search continues. Even a single detection would revolutionize our understanding, confirming that our bubble is not alone. But the cosmic bubble also raises philosophical questions. If we can never see beyond our horizon, can we ever claim to understand the universe as a whole? Are we like inhabitants of a small island, inferring the existence of oceans and continents from the waves that wash ashore? Never able to confirm our theories by direct observation? In some sense, yes. Our knowledge of the cosmos will always be incomplete, limited by the boundaries of light and time. But incompleteness doesn't mean ignorance. Within our bubble, we've made extraordinary discoveries. We've measured the age of the universe, traced the formation of galaxies, detected gravitational waves, and mapped the cosmic web. We've learned that the same physical laws govern everything from atoms to superclusters, that reality operates on principles we can understand, test, and predict. The James Webb Space Telescope exemplifies this pursuit. By capturing light from the earliest galaxies, JWST reveals how structure formed, how stars ignited, how the universe evolved from simplicity to complexity. These discoveries don't tell us what lies beyond the horizon, but they show us the processes, the mechanisms, the laws that govern our region of space. And if the cosmological principle holds, if the universe is homogeneous on large scales, then these same laws likely apply everywhere, even in regions we can never see. As cosmologist Max Tegmark argues, the fact that we can understand the universe at all, even within our limited bubble, is itself remarkable. We are creatures of matter and energy, patterns of atoms that can reflect on their own existence, probe the depths of space, and ask questions about infinity. The cosmic horizon doesn't diminish this achievement. If anything, it amplifies it, reminding us that our knowledge, limited as it is still knowledge, hard-won and profound. But living in a cosmic bubble also means accepting mystery. There are questions we can never answer. Is the universe infinite? What lies beyond our horizon? Are there other bubbles with different physics? These questions might remain forever unanswered, not because we lack the will to pursue them, but because the answers lie beyond the reach of light and time. Yet, mystery isn't failure. It's an invitation, a reminder that the cosmos is larger than our understanding, that reality extends beyond what we can measure or observe. Physicist Richard Feynman once said, "I would rather have questions that can't be answered than answers that can't be questioned." The edge of the observable universe gives us both. Questions that push the boundaries of thought and answers that reveal the workings of nature. NASA's future missions, including the Nancy Grace Roman Space Telescope and next-generation gravitational wave observatories, will continue to explore our cosmic bubble. They'll map dark matter, trace the influence of dark energy, and search for signs of the earliest stars. But they won't eliminate the horizon. The edge will always be there, a boundary we can approach but never cross, a line in space-time that separates the knowable from the unknowable. And perhaps that's fitting. Perhaps the universe was always meant to hold secrets, to extend beyond what any observer can see. The cosmic horizon isn't a limitation, it's a feature, a reminder that reality is larger than perception, that existence outstrips observation. Take a long, slow breath. You are inside the bubble, a tiny point in a sphere of light stretching 46.5 billion light years in every direction. Beyond that edge lies more space, more galaxies, more wonders, all hidden from view by the simple fact that light takes time to travel and space is expanding. You will never see those regions. No one will. They exist if the cosmological principle holds, but they exist beyond the boundary of the knowable. And yet, here you are, inside the bubble, breathing, thinking, wondering, a pattern of atoms that can ask where the universe ends, even if the answer is forever beyond reach. The cosmos has given you this sphere of visibility, this window onto existence, and within it lies more than enough to fill a lifetime of curiosity, more than enough to inspire awe, more than enough to remind you that you are part of something vast, ancient, and endlessly strange. The edge of the observable universe is not an ending, it's a beginning, the starting point for questions that might never be answered, mysteries that might never be solved. And in that space between knowing and unknowing, between the visible and the hidden, we find the essence of what it means to be human, to live, briefly, in a universe that extends far beyond what we can ever see. Conclusion: the horizon that defines us, so we return to where we began, the edge of the observable universe, a boundary, 46.5 billion light-years away in every direction, marks the limit of what we can ever know. Beyond it lies more space, perhaps infinite, perhaps filled with galaxies like ours, or perhaps something stranger, something we can't imagine. We'll never know. The expansion of space driven by dark energy ensures that some regions will forever remain hidden, their light never reaching us, their stories never told. But this limitation, this cosmic blindness, doesn't diminish what we've learned. Within our bubble, we've traced the history of the universe from the Big Bang to the present, mapped the web of galaxies, discovered dark matter and dark energy, and glimpsed the earliest stars. We've learned that we are made of stardust, that the atoms in our bodies were forged in dying stars, that we are the universe made conscious, looking back at itself. The edge of the observable universe is a reminder of both our smallness and our significance. We are small, confined to a single planet, in a single galaxy, in a single corner of a cosmic bubble. But we are also significant because we can ask these questions, probe these mysteries, and understand, at least in part, the nature of reality. As you drift off tonight, beneath the invisible canopy of space, remember this: you are inside the bubble, a sphere of light carved from infinity. Beyond it lies the unknown, vast and hidden. But within it lies everything you need, every star, every galaxy, every moment of beauty and wonder. The universe has given you this view, this window onto existence, and it is enough if this quiet journey has brought you even a small moment of peace. I'm deeply grateful you've spent it here with me. A gentle like or a soft tap on subscribe means more than you can imagine. It's what keeps me creating these cosmic lullabies for wandering minds like yours. And if you're kind enough, please tell me in the comments where you are tonight and what time it is where you're listening. I love seeing how far these quiet adventures drift across the world, from one sleepy corner of the planet to another. Your words, your presence, even your silence, they're like little stars guiding me forward, and I treasure them deeply. Until next time, may the universe hold you gently. May the vastness remind you of your place within it, and may the edge of the observable universe, forever beyond reach, inspire you to wonder at the mysteries that lie beyond what we can ever see.